Here's a question that might break your brain. If the universe contains everything that exists, every star, every galaxy, every atom, even space and time themselves, then what exactly is it expanding into? Scientists have confirmed the universe is expanding and that expansion is actually accelerating. But if there's nothing outside the universe, no empty space waiting to be filled, then how can it expand? If you're ready to question everything you thought you knew about space, time, and existence, make sure to subscribe to this channel and hit the thumbs up. Now let's begin. To understand what the universe is expanding into, we first need to grasp what we mean by the universe and what we mean by expansion. These concepts are nothing like our everyday experience suggests. When we say the universe is expanding, we don't mean that galaxies are flying apart through space like shrapnel from an explosion. Instead, space itself is stretching. New space is literally being created between galaxies every second. This discovery didn't come easily. In the 1920s, Edwin Hubble made observations that changed everything. Using the Mount Wilson Observatory's 100-inch telescope, he noticed that almost every galaxy was moving away from us, and the farther away a galaxy was, the faster it appeared to be receding. This relationship, now known as Hubble's law, was the first concrete evidence that our universe is expanding. But here's where our everyday intuition fails us completely. When we think of expansion, we imagine something expanding into empty space that already exists, like a balloon inflating inside a room. The universe's expansion is fundamentally different. There is no room. There is no pre-existing space waiting to be filled. Space itself is being created as the universe expands. Let me blow your mind with an analogy that cosmologists love, though it's still imperfect. Imagine you're a two-dimensional being living on the surface of a balloon. Your entire universe is that two-dimensional surface. You can't perceive or even conceive of the third dimension. As someone inflates the balloon, your universe expands. Every point on the surface moves away from every other point. But from your two-dimensional perspective, there's no into that you're expanding. The expansion just happens. Now add one more dimension to this analogy. We're three-dimensional beings experiencing a three-dimensional space that's expanding. Just as the two-dimensional surface of the balloon doesn't expand into anything from the perspective of beings confined to that surface, our three-dimensional universe doesn't need to expand into anything. The expansion is intrinsic to space itself. Recent observations from the Planck satellite, which mapped the cosmic microwave background radiation with unprecedented precision, have confirmed that the universe is geometrically flat to within 0.4%. This flatness has profound implications for what the universe is expanding into, or rather, why it doesn't need to expand into anything at all. In 2018, the Hubble Space Telescope's measurements refined our understanding of the expansion rate, revealing a puzzling discrepancy known as the Hubble tension. Different methods of measuring the expansion rate give slightly different results, suggesting there might be new physics we don't yet understand about how space itself behaves on cosmic scales. The concept that really scrambles our brains is that the universe might be infinite. If it's infinite, then it's always been infinite, even at the moment of the Big Bang. An infinite universe expanding doesn't mean it's getting more infinite. Infinity doesn't work that way. Instead, it means the density of matter and energy is decreasing as the same amount of stuff occupies an ever-growing volume of space. But wait, if the universe might be infinite, how can it have started from a single point in the Big Bang? This is where our language and intuition completely break down. The Big Bang wasn't an explosion in space, it was an explosion of space. Every point in today's universe was once that single point. The Big Bang happened everywhere simultaneously because everywhere was the same place 13.8 billion years ago. James Webb Space Telescope, launched in 2021, has given us unprecedented views of the early universe, detecting galaxies that formed just a few 100 million years after the Big Bang. These observations are helping us understand how space itself has evolved and expanded over cosmic time. What we're seeing challenges some of our models about how quickly structures could form in the expanding universe. Dark energy adds another layer of mystery to this cosmic puzzle. Discovered in 1998 through observations of distant supernovae, dark energy appears to be causing the expansion of space to accelerate. This means space is being created at an ever-increasing rate. But dark energy isn't pushing galaxies through space, it's creating new space between galaxies. The discovery of dark energy completely revolutionized our understanding of cosmic expansion. Think about this. Roughly 68% of the universe is made of something we can't see, can't touch, and barely understand. Yet it's determining the ultimate fate of everything that exists. The Supernova Cosmology Project and the High-Z Supernova Search Team independently discovered that distant Type Ia supernovae were dimmer than expected, indicating that the expansion of the universe wasn't slowing down as everyone assumed, it was speeding up. This acceleration means that the amount of space being created between galaxies is increasing exponentially. In about 100 billion years, galaxies beyond our local group will have receded so far that their light will no longer be able to reach us. The observable universe will shrink even as the actual universe continues to expand. Future civilizations might look out and see only our local group of galaxies, with no evidence that billions of other galaxies ever existed. But let's tackle the fundamental question head-on. What does it mean for space to expand if there's nothing to expand into? The answer requires us to abandon our intuitive notions about space and nothingness. In physics, nothing doesn't mean what we typically think it means. Even the vacuum of space is seething with quantum fluctuations, particle-antiparticle pairs popping into existence and annihilating in timeframes so brief they don't violate conservation of energy. This quantum foam, as physicists call it, is the backdrop against which our universe exists. The universe doesn't need an outside to expand into because the universe, by definition, is everything. There is no space outside of space. There is no time before or beyond time. These concepts are as meaningless as asking what's north of the North Pole. The North Pole isn't a boundary that something exists beyond. It's simply where the concept of north stops having meaning. Similarly, the universe isn't expanding into some pre-existing void. The expansion is a property of space itself. General relativity, Einstein's theory of gravity, describes space as a dynamic entity that can curve, stretch, and ripple. The equations don't require an external space for our universe to expand into. Mathematics works perfectly with space expanding intrinsically. When we say space is expanding, we mean the metric, the mathematical description of distances between points, is changing. The distance between any 2 points in space is increasing, not because the points are moving through space, but because space itself is growing. Recent observations from the Sloan Digital Sky Survey have mapped millions of galaxies, revealing the large-scale structure of the universe in unprecedented detail. These observations show that galaxies are distributed in a cosmic web of filaments and voids, and this entire structure is expanding. The expansion isn't happening from a central point. It's happening everywhere simultaneously. Every point in space sees itself as the center of expansion, which is only possible because space itself is stretching uniformly. The Atacama Cosmology Telescope in Chile has been measuring tiny fluctuations in the cosmic microwave background radiation, the afterglow of the Big Bang. These measurements reveal that space has been expanding for 13.8 billion years, and the rate of expansion has changed over time. In the early universe, radiation dominated and expansion was decelerating. Then matter took over, continuing the deceleration. But about 5 billion years ago, dark energy became dominant and expansion began accelerating. Here's something that will really twist your mind. The expansion of space doesn't have a speed in the conventional sense. We can measure the expansion rate, currently about 70 kilometers per second per megaparsec. But this isn't a speed through space, it's a rate at which space itself is growing. Galaxies can recede from us faster than the speed of light without violating relativity because they're not moving through space faster than light. Space is being created between us and them. This leads to a profound realization. There are galaxies we can see today whose light was emitted when they were receding from us faster than light speed. How is this possible? The light was emitted into space that was moving toward us, even though the galaxy itself was in space moving away from us faster than light. It's like walking on a moving walkway at an airport. Even if the walkway is moving backward faster than you can walk forward, you can still make progress if you're on a section that's moving toward your destination. The concept of cosmic inflation adds another layer to this mystery. In the first fraction of a second after the Big Bang, specifically between 10 to the negative 36 and 10 to the negative 32 seconds, the universe underwent a period of exponential expansion. During inflation, space expanded by a factor of at least 10 to the 26, possibly much more. This means that regions of space that were subatomic in scale became larger than the observable universe today, all in less time than light could travel across a proton. Alan Guth, who proposed inflation theory in 1980, realized that this rapid expansion could solve several major cosmological puzzles. The horizon problem, why the universe looks the same in all directions despite regions being causally disconnected, is solved because these regions were once close enough to equilibrate before inflation drove them apart. The flatness problem, why the universe's geometry is so close to flat, is solved because inflation would flatten any initial curvature, like inflating a balloon makes its surface appear flatter locally. But inflation raises its own mind-bending questions about what the universe is expanding into. During inflation, space expanded faster than light, much faster. This doesn't violate relativity because, again, it's space itself expanding, not things moving through space. But it does mean that the universe became causally disconnected from itself. Regions that were in contact before inflation are now and forever unable to communicate, separated by distances that light will never be able to traverse. The multiverse theory offers another perspective on what our universe might be expanding into, or rather, what it's part of. According to eternal inflation, proposed by physicists like Andrei Linde and Alexander Vilenkin, inflation never completely stops everywhere. While it ended in our observable universe 13.8 billion years ago, it continues in other regions, constantly creating new pocket universes. Each pocket universe, like ours, expands within this eternally inflating background, but the background itself is expanding even faster. Think about that for a moment. Our entire universe, everything we can see and everything we'll ever be able to see, might be just one bubble in an infinite foam of universes, each with potentially different physical laws and constants. These other universes aren't elsewhere in our space. They exist in regions that have been pushed beyond our cosmic horizon by inflation, forever disconnected from us. The space between these pocket universes is expanding so rapidly that light signals between them can never connect. The Large Hadron Collider has been searching for evidence of extra dimensions that some theories predict. String theory, for instance, suggests our universe might be a three-dimensional brane floating in a higher dimensional space called the bulk. If this is true, then our universe is expanding within this higher dimensional space, but we can't perceive these extra dimensions directly. They're either too small, compactified, or we're confined to our brain like water droplets sliding on a wire. Recent gravitational wave detections by LIGO and Virgo have opened new windows into understanding space itself. When black holes merge, they send ripples through space-time that stretch and squeeze space as they pass. These observations confirm that space is a dynamic, flexible medium that can be distorted and manipulated. If space can ripple and wave, its expansion becomes less mysterious. It's just another way space can change. The cosmic microwave background radiation, first discovered accidentally by Arno Penzias and Robert Wilson in 1964, provides our best snapshot of the early universe. The Planck satellite's measurements show that this radiation is remarkably uniform, with temperature fluctuations of only about 1 part in 100,000. These tiny fluctuations grew into the galaxies and galaxy clusters we see today, all within the expanding fabric of space. But here's where things get even stranger. The observable universe, everything we can see, is about 93 billion light-years in diameter. Wait, you might think, if the universe is only 13.8 billion years old, shouldn't the observable universe be 27.6 billion light-years across? This is where the expansion of space reveals its true nature. The light from the most distant galaxies has been traveling toward us for over 13 billion years, but during that time, space has been expanding, carrying those galaxies even farther away. The galaxies we see at the edge of our observable universe are now about 46 billion light-years away. This brings us to the concept of the particle horizon, the boundary of the observable universe. This isn't a physical edge, it's simply the distance light has been able to travel since the Big Bang, accounting for the expansion of space. Beyond this horizon, there's more universe, possibly infinite, but we can never observe it because light from those regions hasn't had time to reach us. And due to accelerating expansion, there are regions whose light will never reach us, no matter how long we wait. The universe's topology, its overall shape and connectivity, adds another dimension to this puzzle. While locally the universe appears flat, its global topology could be more complex. It could be finite but unbounded, like the surface of a sphere or a torus, donut shape. If you traveled far enough in one direction in such a universe, you might eventually return to your starting point, having circumnavigated the cosmos. Recent analyses of cosmic microwave background data have searched for signs of such exotic topologies, but haven't found conclusive evidence yet. Dark matter, which makes up about 27% of the universe, adds another layer of complexity to cosmic expansion. While dark matter doesn't interact with light, it does interact gravitationally, and it's been crucial in forming the cosmic structures we see. Observations from the Hubble Space Telescope and other instruments show that dark matter forms a cosmic web, with ordinary matter following its gravitational pathways. This invisible scaffolding is also expanding with space, maintaining its structure even as the universe grows. The Vera Rubin Observatory, currently under construction in Chile, will survey the entire visible sky every few nights, tracking how billions of galaxies move and cluster over time. This will give us unprecedented insights into how expansion affects cosmic structure and might reveal surprises about what expansion really means on the largest scales. Quantum mechanics offers another perspective on the nature of space and its expansion. At the Planck scale, about 10 to the negative 35 meters, space might not be smooth but rather a foam of quantum fluctuations. If space is fundamentally quantum mechanical, then its expansion might be the macroscopic manifestation of quantum processes we don't yet understand. Some theories suggest that space itself might be emergent, arising from more fundamental quantum information processes. The holographic principle, developed by physicists like Gerard 't Hooft and Leonard Susskind, suggests that all the information in a volume of space can be encoded on its boundary. If our universe is holographic, then its three-dimensional expansion might be a projection of information processing on a two-dimensional surface. This radically reimagines what expansion means. It might not be a stretching of space, but an increase in the information capacity of the universe's boundary. The relationship between the expansion of space and the nature of time itself opens up even more profound questions. In general relativity, space and time are unified into space-time, and the expansion of space is intimately connected to the flow of time. Some cosmologists have proposed that what we perceive as the expansion of space might actually be better understood as the creation of time. Each moment, new space-time is being created, and what we call expansion is our three-dimensional perception of this four-dimensional process. Recent observations from the Dark Energy Survey have mapped the distribution of galaxies across billions of light-years, revealing how the expansion rate has changed over cosmic history. The data shows that for the first 9 billion years after the Big Bang, the expansion was decelerating due to the gravitational attraction of matter. But around 5 billion years ago, dark energy began to dominate and expansion started accelerating. This transition point tells us something fundamental about the nature of space itself. It can change its behavior based on what fills it. The concept of the cosmological event horizon adds another mind-bending aspect to expansion. Due to accelerating expansion, there's a boundary beyond which we will never be able to see or influence anything, no matter how long we wait. This horizon is currently about 16 billion light-years away. Galaxies crossing this horizon are not gone, they still exist, but they're entering a realm from which no signal can ever reach us again. It's as if the universe is gradually drawing a curtain around us, limiting what we can ever know or explore. Speaking of the mind-boggling scales involved in cosmic expansion, if you want to truly grasp the size of what's expanding, check out my video called "How Big is the Universe?", where we journey from Earth to the cosmic web, exploring the incredible scales that make expansion even more astounding. The link is in the description below and on the card above, and trust me, understanding the universe's true size will completely change how you think about expansion. Now let's dive into one of the most counterintuitive aspects of cosmic expansion: energy conservation. In our everyday experience, energy is always conserved. It can neither be created nor destroyed. But in an expanding universe, things get weird. As space expands, photons traveling through it get stretched, increasing their wavelength and decreasing their energy. Where does this energy go? The uncomfortable answer is that energy conservation doesn't apply globally in general relativity when space-time itself is dynamic. The vacuum energy problem presents one of the biggest mysteries in physics. Quantum field theory predicts that empty space should have an enormous energy density, about 10 to the power of 120 times larger than what we observe. This discrepancy, called the cosmological constant problem, is the worst prediction in the history of physics. If the vacuum really had this much energy, space would be expanding so rapidly that atoms couldn't form. The fact that we exist means something is cancelling out this vacuum energy to an extraordinary precision, but we don't know what or how. Recent measurements from the South Pole Telescope have been studying the cosmic microwave background's polarization, looking for clues about the universe's earliest moments. These observations might reveal whether our universe is truly infinite or just unimaginably large but finite. If it's finite, it doesn't need an edge or boundary, just as Earth's surface is finite but has no edge. You can travel forever on Earth's surface without hitting a boundary, and the same might be true for our universe in 3 dimensions. The concept of eternal inflation suggests something even more radical. The expansion of space might be the default state of existence. In this view, our Big Bang was just a local event where inflation stopped in a small region, creating a bubble of relatively slow expansion, our universe, within an eternally inflating background. This background continues to expand exponentially, constantly spawning new universes. We're not expanding into this background because we're causally disconnected from it, but we're embedded within it. Observations of Type Ia supernovae, which serve as standard candles for measuring cosmic distances, continue to refine our understanding of expansion. The Pantheon Plus analysis, combining observations of over 1,500 supernovae, has confirmed that the expansion is accelerating and has placed tight constraints on the nature of dark energy. These measurements show that dark energy behaves almost exactly like Einstein's cosmological constant, a fixed energy density of space itself that doesn't dilute as space expands. The Euclid Space Telescope, launched by the European Space Agency in 2023, is designed specifically to study dark energy and the expansion of the universe. By mapping billions of galaxies and their distribution, Euclid will help us understand whether dark energy is truly constant or changes over time. If it changes, this could revolutionize our understanding of what space is and why it expands. Here's a thought experiment that illustrates the weirdness of expansion. Imagine two galaxies separated by 100 million light-years. Due to expansion, the space between them is growing at about 2,000 kilometers per second. Now imagine a chain of 1,000 galaxies, each separated by the same distance. The first and last galaxies in this chain are receding from each other at 2 million kilometers per second, faster than light. Yet no individual galaxy is moving through space at anywhere near light speed. This is possible only because space itself is expanding. The anthropic principle offers another perspective on expansion. If the expansion rate were slightly different, the universe would be radically different, too fast, and matter would never have clumped together to form galaxies and stars. Too slow, and the universe would have recollapsed long ago. The fact that we exist to observe the universe means we necessarily find ourselves in a universe with an expansion rate compatible with our existence. This doesn't explain why the rate is what it is, but it explains why we observe this particular value. The relationship between quantum mechanics and cosmic expansion reveals even deeper mysteries. At the quantum scale, the Heisenberg uncertainty principle tells us that energy and time cannot both be precisely determined. This means that at extremely small scales and short time periods, space itself becomes a seething foam of quantum fluctuations. These fluctuations might be the seeds from which the entire expanding universe emerged. The Big Bang itself might have been a quantum fluctuation that, through inflation, grew to cosmic scales. Recent discoveries from the Event Horizon Telescope, which gave us the first images of black holes, provide insights into how space behaves in extreme conditions. Near a black hole's event horizon, space is so warped that it flows inward faster than light. This isn't a contradiction. It's another example of how space itself can do things that objects within space cannot. If space can flow faster than light into a black hole, its expansion at speeds exceeding light becomes less paradoxical. The concept of the de Sitter horizon adds another layer to our understanding. In a universe dominated by dark energy as ours increasingly is, there's a maximum distance at which objects can ever communicate with us. This de Sitter horizon is like a cosmic event horizon beyond which galaxies are receding so fast that their light will never reach us. As the universe continues to expand and accelerate, this horizon slowly shrinks, isolating us in an island of visibility within an ocean of unreachable space. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will conduct a massive survey of galaxies to measure the expansion history of the universe with unprecedented precision. By observing millions of galaxies and tracking how their distances and redshifts relate, This telescope will help us understand whether dark energy has remained constant throughout cosmic history or has evolved, which would fundamentally change our understanding of what drives expansion. Let's consider what happens at the boundary of our observable universe. There isn't a wall or edge, just a horizon beyond which we cannot see. But here's the mind-bending part. Every point in the universe has its own observable universe, its own horizon. An observer in a galaxy at the edge of our observable universe sees us at the edge of theirs. They have their own observable universe that overlaps partially with ours, but extends into regions we can never see. The universe is thus a patchwork of overlapping observable regions, possibly extending infinitely. The flatness problem highlights just how special our universe's expansion rate is. Observations show that the universe is flat to within a fraction of a percent. But flatness is an unstable condition, like balancing a pencil on its point. Any slight deviation from perfect flatness should grow over time. For the universe to be this flat after 13.8 billion years of expansion, it must have been flat to an extraordinary precision in the early universe, about 1 part in 10 to the 60. Inflation theory solves this by proposing that exponential expansion flattened any initial curvature, like inflating a balloon, makes its surface appear flatter. Gravitational lensing observations have revealed something remarkable about expansion. As light from distant galaxies passes by massive objects, it gets bent by their gravity. But because space is expanding during the light's journey, the lensing effect is modified. By studying these modifications, astronomers can measure not just the mass of the lensing object, but also how much space has expanded while the light was traveling. This gives us a way to measure expansion that's independent of other methods. And so far, all methods agree, space really is expanding. The cosmic neutrino background, theoretical particles left over from when the universe was just 1 second old, offers another window into expansion. These neutrinos have been streaming through space for nearly the entire history of the universe, getting stretched by expansion just like light. If we could detect them directly, they're far too low energy for current detectors, they would tell us about expansion during the first seconds after the Big Bang, long before the cosmic microwave background was released. Dark energy's role in expansion becomes even more mysterious when we consider its properties. Unlike matter or radiation, which dilute as space expands, dark energy's density remains constant. This means that as space expands, more dark energy is created. The total amount of dark energy in the universe is increasing. This seems to violate conservation of energy, but remember, in general relativity with dynamic space-time, global energy conservation doesn't apply. Dark energy might be a property of space itself, so creating more space naturally creates more dark energy. The concept of the Big Rip presents one possible future for our expanding universe. If dark energy's strength increases over time, a possibility called phantom energy, the expansion rate could become infinite in finite time. In this scenario, roughly 22 billion years from now, the expansion would become so violent that it would tear apart galaxies, solar systems, atoms, and eventually space-time itself. Space wouldn't just be expanding, it would be literally ripping apart at every point. String theory offers yet another perspective on what the universe might be expanding into. In some versions of string theory, our three-dimensional universe is a membrane, or brain, floating in a higher dimensional space. Other brains, other universes might exist parallel to ours, separated by microscopic distances in these extra dimensions. Our universe's expansion would be the stretching of our brain within this higher dimensional space, though we can only perceive the three-dimensional aspect of this process. The quantum vacuum might hold the key to understanding expansion. Even in the emptiest regions of space, quantum fields fluctuate, creating virtual particles that pop into existence and annihilate. These fluctuations give the vacuum an intrinsic energy and pressure. Remarkably, while the vacuum's energy density is positive, its pressure is negative. This negative pressure is what drives cosmic acceleration. Space essentially pushes itself apart from within. The implications of negative pressure deserve deeper exploration because they completely shatter our everyday intuitions about how things work. In normal matter, positive pressure pushes outward, like air in a balloon. But the quantum vacuum has negative pressure, which in general relativity acts like anti-gravity. This isn't science fiction, it's observed fact. The vacuum of space literally pulls on itself, creating more space. It's as if emptiness has a tendency to create more emptiness, a cosmic hunger that feeds on itself. Recent observations from the Hubble Space Telescope have revealed that expansion affects different types of objects in different ways. Galaxies bound by gravity, like our Milky Way, don't expand internally. Gravity is strong enough to hold them together against the expansion of space. The same is true for galaxy clusters. But in the vast voids between clusters, where gravity is weak, expansion dominates. This means the universe is becoming increasingly fragmented, with islands of matter separated by ever-growing oceans of empty space. The Hubble tension, the disagreement between different measurements of the expansion rate, has become one of the most pressing mysteries in cosmology. Measurements based on the cosmic microwave background give an expansion rate of about 67 kilometers per second per megaparsec, while measurements from supernovae and other local sources give about 73. This discrepancy might seem small, but it's statistically significant and could indicate new physics we don't understand. Consider this mind-bending possibility. What if the expansion rate isn't the same everywhere? Most cosmological models assume the universe is homogeneous and isotropic, the same in all locations and directions. But some recent observations hint at possible variations. The Dark Energy Survey has found tentative evidence that different regions might have slightly different expansion rates. If confirmed, this would revolutionize our understanding of what the universe is expanding into, or rather, how different parts of space can expand at different rates. The James Webb Space Telescope has been observing the most distant galaxies ever seen, some from when the universe was just a few 100 million years old. These observations are revealing surprises about how quickly structures formed in the expanding early universe. Some galaxies appear more massive and mature than expected, suggesting that our models of how expansion affected early structure formation might need revision. The concept of pocket universes within eternal inflation presents a fascinating picture. Each pocket universe, like ours, has its own Big Bang, its own expansion history, and potentially its own laws of physics. These universes aren't expanding into each other, they're causally disconnected, separated by regions of space expanding so rapidly that no signal can cross between them. Our universe might be one of countless bubbles in an infinite foam, each bubble expanding according to its own rules. Quantum entanglement adds another dimension to the mystery of expansion. When particles are entangled, they maintain instantaneous correlations regardless of the distance between them. As space expands and carries entangled particles apart, their quantum connection remains. This suggests that quantum information might be more fundamental than space itself, that space and its expansion might emerge from a deeper layer of quantum relationships. The Wheeler-DeWitt equation, sometimes called the wave function of the universe, attempts to describe the quantum state of the entire cosmos. In this framework, the universe doesn't expand in time. Instead, time emerges from the quantum state itself. The expansion of space and the flow of time are two aspects of the same phenomenon, viewed from within the universe. From this quantum perspective, Asking what the universe expands into is like asking what time flows into. The question assumes a container that doesn't exist. Recent studies of baryon acoustic oscillations, frozen sound waves from the early universe, have provided another way to measure expansion. These oscillations created a characteristic scale in the distribution of galaxies about 500 million light-years across. By measuring this scale at different cosmic epochs, astronomers can track how space has expanded over billions of years. The results confirm that expansion has been accelerating for the past 5 billion years. The possibility of varying constants of nature adds another twist. Some theories suggest that what we call constants, like the speed of light, the strength of gravity, or the masses of elementary particles, might actually vary over cosmic time or in different regions of space. If true, the expansion rate might be linked to these variations. The universe might not just be expanding, it might be evolving its fundamental properties as it grows. Black hole thermodynamics provides unexpected insights into expansion. Stephen Hawking showed that black holes have entropy proportional to their surface area, not their volume. This led to the holographic principle, the idea that the information content of any region is limited by its surface area. Applied to the universe, this suggests that as space expands, it's not creating new volume so much as new surface area for encoding information. The expansion might be fundamentally about increasing the universe's information capacity. The cosmic web, the largest structure in the universe, is being shaped by expansion in fascinating ways. Galaxy filaments are being stretched, but they're also growing through gravitational attraction. Voids are expanding faster than the average expansion rate because they have less matter to slow them down. This creates a complex dance between gravity trying to pull matter together and expansion trying to pull it apart, resulting in the beautiful web-like structure we observe. Observations of the Lyman alpha forest, absorption lines in the spectra of distant quasars reveal that the distribution of hydrogen gas across billions of light-years and billions of years. This gas traces the cosmic web and shows how expansion has affected structure on the largest scales. The data confirms that expansion is not just a large-scale average effect, but operates consistently from the scale of galaxy clusters up to the largest structures we can observe. The relationship between entropy and expansion opens up profound questions about the arrow of time and the ultimate fate of information in our universe. As space expands, the maximum possible entropy of the universe increases. This ever-growing capacity for disorder might be what gives time its direction. We experience time flowing forward because that's the direction in which entropy can increase, and entropy can increase because space is expanding. Without expansion, the universe might reach maximum entropy, and time, in any meaningful sense, would cease to flow. The discovery of supervoids, regions of space containing far fewer galaxies than average, has revealed how expansion affects different regions differently. The Boötes supervoid, spanning 330 million light-years, is expanding faster than regions with normal galaxy density. It's as if the universe has different expansion rates in different places, all embedded within the overall cosmic expansion. These voids are growing emptier and larger, while galaxy clusters resist expansion through gravity, creating an increasingly fragmented cosmos. Recent computer simulations using the world's most powerful supercomputers have modeled how expansion affects the universe on scales we can't directly observe. The Illustris and Eagle simulations track billions of particles over billions of years, showing how expansion interacts with gravity, dark matter, and gas dynamics to create the cosmic structures we see. These simulations reveal that expansion doesn't just make things farther apart, it fundamentally changes how structures can form and evolve. The concept of conformal cyclic cosmology proposed by Sir Roger Penrose suggests something radical. Our expanding universe might be one in an infinite sequence of universes, each beginning with a big bang and ending in infinite expansion. In this model, the infinitely expanded end state of one universe becomes, through a mathematical transformation, the Big Bang of the next. The universe isn't expanding into anything, it's participating in an eternal cycle where expansion itself transforms into new beginnings. Observations of galaxy clusters through the Sunyaev-Zeldovich effect, where cosmic microwave background photons are scattered by hot gas in clusters, provide another window into expansion. As these photons travel through the expanding universe and interact with galaxy clusters at different epochs, they carry information about how expansion has changed over time. The South Pole Telescope and Atacama Cosmology Telescope have used this effect to map expansion's history with increasing precision. The quantum Zeno effect suggests something bizarre about observation and expansion. In quantum mechanics, frequent observation can freeze a system's evolution. Some theorists wonder if consciousness or observation might play a role in cosmic expansion. Could the universe expand differently in regions that are being observed versus regions that aren't? While this remains highly speculative, it highlights how quantum mechanics might fundamentally alter our understanding of expansion. Dark flow, the mysterious motion of galaxy clusters toward a particular region of sky, hints that our observable universe might be influenced by structures beyond our cosmic horizon. If confirmed, this would mean that what we call the universe is just a small part of something much larger, and our local expansion is affected by massive structures we can never see. The universe might not be expanding uniformly, but could be part of an even larger scale flow or expansion pattern. The possibility of cosmic topology remains one of the most intriguing unknowns. While the universe appears flat and infinite locally, it could have a more complex global structure. It might be a three-dimensional torus where traveling far enough in one direction brings you back to your starting point. Or it could have a more exotic topology with multiple connections. In such universes, expansion would have a very different meaning. Space would be finite but unbounded, expanding into itself rather than into anything external. Recent measurements of the integrated Sachs-Wolf effect, where cosmic microwave background photons gain or lose energy passing through evolving gravitational wells, provide direct evidence of dark energy's effect on expansion. As the universe expands and structures evolve, photons traveling through them experience shifting gravitational fields. This effect, predicted by general relativity and confirmed by observations, shows that expansion affects even the propagation of light through seemingly empty space. The concept of the multiverse radically reframes what expansion means. In the many worlds interpretation of quantum mechanics, every quantum event branches the universe. In this view, the universe isn't just expanding spatially, it's constantly branching into parallel realities. Each branch has its own expansion history, and what we call cosmic expansion might be just one aspect of a far more complex multiplication of realities. Observations of time dilation in distant supernovae provide direct evidence that expansion affects time itself. Supernovae in distant galaxies appear to evolve more slowly than nearby ones, not because the physics is different, but because time itself is stretched by expansion. A supernova that would take 20 days to fade in a nearby galaxy takes 30 days in a galaxy billions of light years away. We're literally watching the universe's expansion stretch time. The discovery of dark energy stars, hypothetical objects that could mimic black holes, raises questions about whether expansion could be prevented locally by exotic matter. If regions of space could resist expansion completely, they would become increasingly dense relative to the expanding universe around them. Over cosmic time, these regions might become isolated islands of non-expanding space in an ever-expanding cosmos. The relationship between information and expansion suggests something profound about reality's nature. As the universe expands and cools, it can support increasingly complex information structures, from particles to atoms to molecules to life to consciousness. Expansion might not just be about space getting bigger, it might be about the universe increasing its capacity for complexity and information processing. We exist because expansion has created the conditions for our level of complexity to emerge. The phenomenon of cosmic inflation provides our best explanation for why the universe appears so uniform on large scales, but it also raises profound questions about the nature of expansion itself. During inflation, space expanded by a factor of at least 10 to the 26 in about 10 to the negative 32 seconds. This means regions smaller than a proton became larger than the observable universe. If space can expand this rapidly, what exactly is doing the expanding? The inflaton field, hypothesized to drive inflation, suggests that space expansion can be powered by quantum fields we haven't yet detected. Recent observations from the BICEP Keck array at the South Pole have been searching for primordial gravitational waves, ripples in spacetime from the inflation epoch. While earlier claims of detection turned out to be contamination from galactic dust, the search continues with ever-increasing sensitivity. If detected, these primordial waves would tell us about the universe when it was 10 to the negative 35 seconds old, when the entire observable universe was smaller than an atom, yet expanding faster than we can truly comprehend. The concept of emergent spacetime suggests that space and time themselves might not be fundamental, but could emerge from something deeper. Loop quantum gravity proposes that spacetime is made of discrete loops at the Planck scale. In this view, expansion isn't stretching a continuous fabric, but rather creating new loops, adding new nodes to the quantum network that is space. The universe isn't expanding into anything, because space itself is being created at the quantum level. Studies of distant gamma-ray bursts have placed stringent limits on whether space-time is fundamentally smooth or discrete. If space is made of discrete units, photons of different energies should travel at slightly different speeds over cosmic distances. The Fermi Gamma-Ray Space Telescope has observed bursts from billions of light-years away, with high and low-energy photons arriving within milliseconds of each other. This suggests that if space is discrete, the scale is at least 1,000 times smaller than the Planck length. The thermodynamic arrow of time and cosmic expansion are intimately connected in ways we're only beginning to understand. The second law of thermodynamics says entropy always increases, but this is only possible because the universe started in a low entropy state and has room to increase entropy as it expands. Without expansion, the universe would reach thermal equilibrium, maximum entropy, and nothing interesting could happen. Expansion creates the gradients and disequilibrium necessary for stars to shine, planets to form, and life to evolve. The possibility of phantom energy presents one of the most extreme scenarios for future expansion. If dark energy's equation of state parameter is less than -1, its density will increase as the universe expands. This would lead to ever-accelerating expansion, eventually overcoming all forces. In the Big Rip scenario, expansion would become so violent that it would tear apart galaxy clusters, then galaxies, then solar systems, then atoms, and finally, space-time itself would be ripped apart at every point. Observations of the cosmic web's evolution over billions of years reveal how expansion shapes the largest structures in the universe. The Dark Energy Spectroscopic Instrument, DESI, is creating a three-dimensional map of tens of millions of galaxies, tracking how expansion has affected structure formation across cosmic time. Early results show that voids are expanding faster than predicted, while filaments are more resilient to expansion than expected, suggesting our models of how expansion interacts with gravity need refinement. The holographic principle applied to cosmology suggests that our three-dimensional universe might be encoded on a two-dimensional surface at the cosmic horizon. As the universe expands, this surface area increases, allowing for more information to be encoded. In this view, expansion is fundamentally about increasing the universe's information storage capacity. We perceive this information increase as three-dimensional spatial expansion, but it might be more accurate to think of it as the universe's computational capacity growing. Recent studies of ultra-diffuse galaxies have revealed objects that seem barely held together, with stars spread over areas as large as the Milky Way, but containing only 1% as many stars. These galaxies appear to be on the verge of being torn apart by expansion. They represent a boundary condition, objects just barely able to resist the universe's expansion through gravity. Their existence helps us understand the precise balance between expansion and gravitational binding. The concept of the Hubble bubble suggests we might live in a region of space with different properties than the cosmic average. Some observations hint that our local region, extending hundreds of millions of light-years, might have a slightly different expansion rate or matter density than the broader universe. If true, this would mean that our measurements of cosmic expansion are biased by our location, and the universe might be even stranger than we think. Quantum decoherence and expansion might be fundamentally linked. As the universe expands and quantum systems become more separated, they decohere, lose their quantum properties, and become classical. This suggests that expansion might be what transforms the quantum fuzziness of the early universe into the classical, definite reality we observe. The universe might need to expand for classical physics to emerge from quantum mechanics. The possibility of cyclic cosmologies offers another perspective on what expansion means. In these models, the universe goes through infinite cycles of expansion and contraction, or expansion and regeneration. Each cycle might have different properties, different physical laws, or different amounts of matter and energy. Our current expansion phase would be just one movement in an eternal cosmic symphony, with no need for an outside to expand into. The relationship between consciousness and cosmic expansion presents one of the most profound mysteries in science. Some interpretations of quantum mechanics suggest that observation collapses wave functions, transforming quantum possibilities into classical realities. If consciousness plays a fundamental role in quantum mechanics, and if the universe is fundamentally quantum mechanical, then the expansion of space might be creating new venues for observation and consciousness. The universe might not just be expanding its physical volume, but its capacity for awareness and observation. Recent discoveries about fast radio bursts, mysterious millisecond pulses of radio waves from distant galaxies, have provided new tools for studying expansion. As these bursts travel through the expanding universe, they interact with intervening matter in ways that encode information about expansion history. The dispersion of different frequencies tells us about the density of matter along the path, while the timing tells us about distances. These cosmic lighthouses are helping us map expansion with unprecedented precision. The concept of the cosmic web's skeletal structure reveals how expansion creates vast cosmic voids while simultaneously allowing matter to condense along filaments. Computer simulations show that without expansion, matter would either uniformly fill space or collapse into massive black holes. Expansion provides the perfect balance, creating a cosmic foam structure where matter can organize into galaxies along filament intersections while voids expand and empty. This structure wouldn't exist without precisely the right expansion rate. Studies of ancient quasars powered by supermassive black holes have revealed something remarkable about the early universe's expansion. These quasars existed when the universe was less than 1 billion years old, yet they contain black holes with billions of solar masses. For these black holes to grow so large so quickly, the early universe's expansion must have allowed for very specific conditions, dense enough for rapid accretion, but not so dense that everything collapsed. The existence of these ancient giants constrains what expansion could have been like in the universe's youth. The possibility that we live in a false vacuum adds an existential dimension to cosmic expansion. If the Higgs field exists in a metastable state rather than its true minimum, the universe could undergo vacuum decay, with a bubble of true vacuum expanding at the speed of light, destroying everything in its path. Cosmic expansion might be protecting us by diluting the probability of such an event and carrying potential nucleation sites beyond our cosmic horizon. Observations of the Laniakea supercluster, our home supercluster, spanning 500 million light-years, show how expansion affects the largest gravitationally bound structures. While the supercluster as a whole is being stretched by expansion, its core regions resist through gravity. This creates a complex flow pattern, with galaxies streaming toward the center, while the outer regions are carried away by expansion. We're witnessing a cosmic tug-of-war between gravity and expansion on the largest scales. The discovery of galaxies that appear to lack dark matter challenges our understanding of how expansion and structure formation interact. These galaxies, like NGC 1052 DF2, seem to have formed through processes we don't understand, possibly involving high-speed collisions or tidal stripping in the expanding universe. Their existence suggests that expansion might create conditions for exotic structure formation that our models haven't predicted. Recent measurements of the kinetic Sunyaev-Zeldovich effect have revealed the peculiar velocities of galaxy clusters, their motion relative to the expanding cosmic frame. These measurements show that clusters move at hundreds of kilometers per second relative to the cosmic expansion, drawn by the gravity of surrounding structures. This cosmic dance, superimposed on overall expansion, creates a complex pattern of motion that we're only beginning to map. The concept of eternal inflation suggests that what we call the Big Bang was just our local region transitioning from inflation to slower expansion. In this view, most of space is still inflating at an exponential rate, constantly spawning new pocket universes like ours. Our universe isn't expanding into this inflating background. We're causally disconnected from it. But we're embedded within it like a bubble in an infinite foam where most bubbles are still forming. Time dilation due to expansion has observable consequences that seem almost like science fiction. When we observe a galaxy 10 billion light-years away, we're not just seeing it as it was 10 billion years ago, we're seeing its time running slower relative to us. A clock in that distant galaxy would appear to tick slower from our perspective, not because of relative motion through space, but because of the expansion of space between us. The universe's expansion literally stretches time itself. The possibility of domain walls, defects in space-time left over from phase transitions in the early universe, could create regions with different expansion properties. If such walls exist, crossing one could mean entering a region where the fundamental constants, including those governing expansion, are different. These walls would be expanding with space, potentially creating isolated regions with their own expansion histories. Observations of cosmic voids with the Dark Energy Survey have revealed that these empty regions aren't truly empty, but contain a sparse network of dwarf galaxies and gas filaments. These voids are expanding faster than the cosmic average, effectively pushing matter toward the surrounding walls and filaments. This void expansion might be a key driver of cosmic structure formation, sculpting the universe's large-scale architecture through differential expansion rates. The relationship between black holes and expansion presents fascinating paradoxes. While space expands everywhere else, it contracts near black holes. At the event horizon, space flows inward faster than light. This creates regions where expansion is not just halted, but reversed. As the universe expands and dilutes, black holes become increasingly dominant in their local regions, creating islands of contraction in an expanding cosmos. As we reach the culmination of our journey through this cosmic mystery, let's confront the deepest implications of what we've discovered. The universe isn't expanding into anything, because the universe is, by definition, everything that exists. There is no space outside of space, no time beyond time. The expansion is not a movement through some pre-existing void, but the creation of space-time itself. This isn't just a scientific fact, it's a profound philosophical revelation that challenges the very foundations of how we think about existence. The ultimate fate of our expanding universe depends on the nature of dark energy, and recent observations have narrowed the possibilities while raising new questions. If dark energy remains constant, we face the heat death scenario, eternal expansion leading to a cold, empty universe where all stars have died, all black holes have evaporated through Hawking radiation, and only elementary particles remain in an ever-diluting soup. The timescales are staggering. The last stars will die in about 100 trillion years, the last black holes will evaporate in 10 to the 100 years, and beyond that lies an eternity of cold, dark expansion. But there's something beautiful hidden in this seemingly bleak future. As Sir Roger Penrose has pointed out, in the far future when only photons remain, the universe loses all sense of scale and time. A universe containing only photons expanding forever becomes, through a mathematical transformation called conformal rescaling, indistinguishable from a hot, dense state, potentially the Big Bang of a new universe. Expansion might not be a one-way journey to emptiness, but part of an eternal cycle where endings become beginnings. The discovery that we can only ever observe a finite portion of a potentially infinite universe has profound implications for science and philosophy. If the universe is infinite, then everything that can happen must happen somewhere. There are infinite copies of Earth with infinite variations, worlds where history unfolded differently, where you made different choices, where the laws of physics might even be subtly different. The expansion of space ensures these regions remain forever isolated, each playing out its own cosmic story. Recent observations from the James Webb Space Telescope have revealed galaxies that challenge our models of early cosmic expansion. Some galaxies appear too massive and too mature for their age, suggesting that our understanding of how expansion affected early structure formation needs revision. These discoveries remind us that despite our sophisticated theories, the universe continues to surprise us. Each new observation is an opportunity to refine our understanding of expansion and its consequences. The quantum vacuum, seething with virtual particles and quantum fluctuations, might hold the key to understanding why space expands at all. The vacuum isn't nothing, it's a complex quantum system with energy, pressure, and dynamics we're only beginning to understand. Some theories suggest that what we call dark energy is simply the gravitational effect of vacuum fluctuations. The universe might be expanding because emptiness itself has an inherent tendency to grow, a cosmic restlessness built into the fabric of reality. The anthropic principle, when applied to expansion, reveals just how fine-tuned our universe appears to be. If the expansion rate in the early universe had been different by 1 part in 10 to the 60, we wouldn't exist. Too fast, and matter would never have clumped into galaxies. Too slow, and the universe would have recollapsed before stars could form. This extraordinary precision has led some scientists to propose that our universe is one of countless others, each with different expansion rates, and we naturally find ourselves in one compatible with our existence. The holographic principle suggests that all the information in our 3-dimensional universe might be encoded on a 2-dimensional surface at the cosmic horizon. As the universe expands, this surface grows, allowing for more information, more complexity, more possibilities, more experiences. In this view, expansion is fundamentally about increasing the universe's capacity for information and complexity. We exist because expansion has created enough room in information space for structures as complex as human beings to emerge. Looking at the larger scales, we see that expansion has created a universe of breathtaking beauty and complexity. From the quantum foam at the Planck scale to the cosmic web spanning billions of light years, from the first quantum fluctuations to the emergence of consciousness, expansion has been the canvas on which the story of existence is painted. Without expansion, there would be no stars, no planets, no life, no awareness, just an eternal, unchanging uniformity. The fact that we can even ask what the universe is expanding into represents a triumph of human consciousness. We are arrangements of atoms that have become aware, capable of contemplating the cosmos that created us. Through science, we've discovered that we live in an expanding universe without edges or boundaries, a cosmos that creates its own space and time as it grows. This knowledge doesn't diminish us, it elevates us as participants in the grandest possible story. As you go about your daily life, remember that you're embedded in an expanding cosmos. The space between galaxies is growing. The cosmic web is evolving. New space is being created every moment. You're not a separate observer watching this happen, you're part of it. The atoms in your body, the thoughts in your mind, the very ground beneath your feet are all participants in this cosmic expansion. You are the universe becoming aware of itself, asking questions about its own nature. The mystery of what the universe is expanding into ultimately points us back to ourselves. In trying to understand cosmic expansion, we're forced to confront the limits of human intuition and the power of mathematical physics to transcend those limits. We've learned that reality is far stranger and more wonderful than our everyday experience suggests. The universe doesn't need to expand into anything because existence itself is more profound than our simple notions of space and containment. This is the gift of contemplating cosmic expansion. It expands our minds. It shows us that reality operates on principles that challenge our assumptions while following mathematical laws of stunning beauty. It connects us to the cosmos in ways both humbling and empowering. We are finite beings capable of comprehending the infinite mortal creatures who can grasp eternity, tiny specks of matter that can understand the universe that created us. And in that understanding, we find our place in the cosmic story, not as outside observers, but as the universe understanding itself. If you are still watching, make sure to subscribe to the channel and give a thumbs up. And if you enjoyed this video, I am sure you will love this other one at the left side of the screen. This is Why We Will Never Reach Mars. Explore the brutal realities of Mars missions, from deadly cosmic radiation, toxic Martian dust, and bone-crushing gravity problems to the insurmountable challenges of food, water, and life support on the red planet.